So, good morning, and today we continue our study of the photon gas. And so, we derived this formula for the energy density, which we expressed in terms of this integral or omega or frequency, and this I of omega was identified with the intensity. Okay, and if you plot it, you get this thing. And so we saw how beautifully the Kobe data for the cosmic microwave background radiation fitted this curve. Okay, and before I forgot to mention that Penzias and Wilson won the Nobel Prize in Physics in the 1970s. It's either 76 or 78, I don't remember exactly. And I would suggest that you go and listen to their Nobel speeches, and there are lots of popular accounts of that thing on there's a thing called nobelprize.org where you can. Okay, so okay, this I really enjoy uh, many of the things material that is given out on this site, and so it's worth looking at Penzias Wilson. And okay, so the fits were so good that we cannot even see the error bars, unless of course they are amplified. Okay, and in the graph yesterday we saw it was amplified 400 times or something like that. Okay, so today what we are going to do is we will continue with today we will just we will continue with a conventional study. Okay, of the photon gas. Okay, and so of course in the grand canonical form. So we have this Q, which would be the product for all the energies, and lambda is the polarizations. Takes only two values, but okay. For all the energies and lambdas times 1 minus what should I write here? Actually, what was the expression for Q? Okay, so let's recall what we would write. Okay, anyway, I'll just write it. Epsilon time right? This is inverse. Does anybody remember what this formula? It said that you consider every thing. So the states, so every state is labeled by energy maybe, and some momentum and things like that. So lambda, etc. And so we treated it like a box, and so there can be 1, 0, 1, 2, 3, so on and so forth particles, and we added a geometric series. Okay, so so phi would be minus kbt log of q. Okay, so the log is important. It converts this pi into a product, into a summation, so it becomes, there's a minus here and there is also a minus here, so you get a plus kbt into sum over epsilon and lambda. Actually, it shouldn't be epsilon and lambda over all states. Okay, but I'm writing it, so I'll have to put the density of states. G of epsilon. So this is just the degeneracy factor. Okay. Okay, this is what we get. And so we take the continuum limit, and so this fellow I'll just replace with integral of 0 to infinity d omega rho of omega. Okay, so we get our formula for phi. Okay, I kept the mu, but I'll put mu equal to 0 in a moment. But we spent some time arguing that thing. So we get phi equal to kbt into log integral 0 to infinity d omega rho of omega, which we worked out last time. So what was rho of omega? So we can get it from here. Is just remove the h bar omega, so it's omega squared upon pi square c cubed. And I'll put a factor of 2 for the polarization. Okay, is this fine? So this is the grand canonical partition function that we get. And I forgot a factor of v, because here I divide out by v, so this is what we get. Okay, maybe I should write the v outside. So what is it we want? So let us now work out what is the pressure. P equal to, is it d phi by dv or d minus d phi by dv? Let me write something. Okay, now I have set mu equal to 0. Okay. The reason to not set mu equal to 0 right away is that if you want to get the average number, what is it? So there's a minus sign, I think. So let's put that in here. And so now, so what we need to do is, so this is the expression for the pressure, and yeah, okay. I have set mu equal to 0. The reason I didn't want to do this is that if you want to get number from here, we have to write d phi by d mu and then set mu equal to 0. Okay, so then that will give us the average number. Okay, so that's the reason to keep mu here. But when I wrote it here, I didn't need to do this thing. So let us Now what I want to show is I want to prove that P equal to 1/3 times U by V, or little u. Okay, so what is it we have to do? We have to do some integration by parts. So let me do that. And so what I want is something like this. I so I, so I'll use this formula, which is integral u dv equal to minus integral v du plus uv evaluated at the endpoints. Okay, so I have to choose u and v appropriately. So please help me, because what I want to do is I want to get rid of the log. So I want to take u to be, say, log of 1 minus, and epsilon is h bar omega. Okay. And what is dv? I can take it to be omega square d omega. Don't worry about the pi square c cubed. I'll pull that out. Is this fine? Okay. So let's do this integration. So we get p equal to, what was the terms? Minus 2 kbt now open brackets, and first thing to do is v du. So we have tried v du. So minus integral v is omega cubed by 3 du, which is 1 by 1 minus e power minus beta h cross omega times e. Then we have to take the derivative, so it will get, there's one more, there are a couple of minus signs which I'll just ignore. Okay, plus uv Okay, so let's look at what happens at the endpoints. Okay, at omega equal to infinity, u is 0. Okay, so, and u, oh, thank you, thank you. Perfect. Is that you, Bidhi? Okay. Kanika, is it? Okay, good. Thank you. Okay, so this term vanishes. You can check this. Okay, and now you can see this beta will go and cancel off this thing. The two minus signs go off. So if I write this thing, I get 2 by 3 pi square c cubed, okay, into all the signs go off, integral, and I can pull out the h bar also. And I can re-express it like this. Is this okay? Now if you go back and compare it with u by v, which we started off with, sorry, I have to go so many things. It's exactly that, right? Okay, so where did the 2 come from? Here also I forgot the 2. 2 is the polarization, right? That's there even in this case. Or I made 2 mistakes. So no, this is 2 is not there. The 2 is not here. I put it twice because it already has that. That's the row. Okay. Okay, very good. Okay. So now we can see, after integrating by parts, surface terms vanish. What is this equal to? Other than this factor, it is 1/3 times u by v. Okay, so compare with ideal gas. where we got P equal to 2/3 U by V. Okay, so really the reason this is happening is because epsilon goes as, okay, so the reason is the following: epsilon goes like P power, say some alpha. Okay, so alpha equal to 1 for massless photon, massless particles, relativistic particles, and alpha equal to 2 for non-relativistic. Okay, so it turns out that you can show exercise, one can show that for this dispersion relation, for the dispersion relation, epsilon going as P power alpha, there can be factors, P equal to, I guess, alpha by 3 U by V. Okay, so another case would be phonons. You can work out what is phonon situation. Phonons also have alpha equal to 1, so you should get 1/3. So you try to prove this. Try to prove this. Okay. Okay. So this is what I think is the reason. But anyway, no, but it's actually true. Okay, so this is also true. So what you will see is that I'm sorry, there are two P's here. This is momentum, magnitude of momentum. Okay, and this capital P is the pressure. Okay, so this is something which we can prove. So so is this clear? What? The two went because I made a mistake. I was copying some formula, and I put a 2 over and above that. So this expression for U, I don't remember rho and all. So I was just looking at this and extracting it, and then I over and above that I put a factor of 2. This already has the polarization factor put in, so I don't need to put an extra. Okay, otherwise you would have given 2/3. Okay, so we will show. Actually, we will also see that this P equal to 2/3 U holds for gases, quantum gases or fermions, and okay, as long as they're relativistic, non-relativistic. Okay, then epsilon is just P square, right, upon 2. Okay, so so just uh, one more. So one thing which I wrote blissfully is that the photon gas exerts a pressure, as we just saw. This is usually called the radiation pressure. But the thing is that so radiation pressure can be understood in the continuum in classical electrodynamics also, but in the quantum situation, so we see the particle picture is nice in the sense that in the particle photon description, of electromagnetic radiation, we can understand pressure as arising from photons bouncing off the walls elastically. This is energy being conserved. Okay, so this is something which is very nice in the photon description. Okay, so now that we have this thing, so one thing we did not do last time is to work out what is the average. We said that the number of photons is not fixed, but we can ask what is the average number. Okay, so what we want is n. That would be integral 0 to infinity d omega rho of omega n of omega, which is 1 by, okay, and what is rho of omega? Yeah, c cubed, right? So 2's cancel. I wrote it. Okay, so this is what we have, and so we can just go ahead and write this out, plug that in, and we get n equal to. So we can pull out various terms. V by pi square c cubed I can pull out, and we get 0 to omega infinity d okay, this is what we get. And so now we can just scale. So the only beta, so we can rescale. We can introduce a new variable. Let's say we call it x. We'll just define it to be beta h cross omega, or we call it xi many times a day. So let's call it xi. Okay. So what we get is d xi equal to beta h bar times d omega, or d omega equal to, so we get n by v, number density. So there will be 3 powers of beta h bar omega. So we'll just get v This is okay. This is what we get. What 1 by pi square? Oh, yeah. Thanks. Okay. Okay. So now we just go ahead and let's expand this. So what is it we want to do? We will expand this as a power series in xi. So yeah. So this is just some integral, but one thing we can see is that the number. So there's a beta here. So n by v is proportional to t cubed. Okay. And you can, this is some finite integral, and one can show that n by v. So compute this integral and show that n by v is equal to, this others are all constant, which you can work out what they are, is equal to, okay, sorry, I have it in a particular form. H, not h bar. Okay, so just check that. I mean, this is just a numerical value that you can get. Okay, so one more thing is, so this is, so we get, so so there is, so this is just the average number density, and it goes like t cubed. So it says as t increases. We could also go back and look at, let's look at how, u by v depends on temperature. Okay, so we go back there, and so now I won't do the detailed calculation, but we can come back here, and it's almost the same as this, but there's an extra factor of omega. So here we have u by v. So again, we can scale things out. So here is the same scaling, but previously we had omega square, now we have omega cubed. So you will see that you'll get an extra power of beta. Okay, so I'll give it as an exercise. Okay, so exercise. So no, wait. So let's write this first. It is easy to see that u by v, that's the energy density, is proportional to t power 4. Okay, so, or we can write this as u by v equal to sigma t power 4. Okay, the t cube became t power 4 because here we had only xi square, there you'll get xi cubed. Okay, so that's the only change. There are factors of h bar, etc., that you can work out. And this law as a name, again, you would have learned it in high school. It says that the energy density of black body radiation is proportional to the fourth power of the temperature. What is this law called? What? Law. So Wien's displacement law says where the peak shifts as a function of lambda. It says lambda peak times temperature equal to constant. Okay, that is was an exercise. Okay, so exercise is determine sigma exactly. Sigma. So you have to put all the factors together. Okay. So this is the Stefan Boltzmann law. And this constant is called Stefan's constant. Yeah. Yes. Mm. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Very good. Very good. Why? Because there is a problem. Because there is a problem at 0 for the integral. No, but it should be expressed. You can do it because what is happening? It's not blowing up at 0, right? Because e power minus xi equal to 0 denominator goes as xi, but numerator goes as xi square. So there's no problem. For large xi also it is fine. So we know this function will be. So this function will look like this. There should be no problem. It will go like quadratic like this. P can come down. So it will have some finite. Okay. A numerical guy, I mean, if you want, you just shift this, instead of 0, you put some number 1 or something. See what you get. Okay. So it's not treating 0 correctly. This is what I feel. Okay. So another way of, yeah, you can, I won't, I think it should work. I mean, this is a finite integral. You agree, right? I mean, you see that so for large values of xi, this will dominate. This will take over greater than 1. And it's less than 1, you need to do something, but it doesn't matter. It will be this part of the thing. Okay. So basically, this will have this plot. And near this thing, it will be linear actually, xi. So actually, I shouldn't draw it. I drew it wrong. So let me fix that. So it will be linear and then okay. So it should be finite. The integral doesn't diverge that much, I know. Huh? Yeah. Yeah, it should be zeta of 3. Yeah. Yeah, yeah. I know it's zeta of 3. So this is, you can show that, you can actually prove that. Okay. You're saying it is 2 zeta of 3, is it? Okay, that's possible. Okay, so zeta of s is just defined as summation n equal to 1 to infinity 1 by n power s. And so this is convergent for s, real part of s actually greater than 1. Okay, so this is called the zeta function. Okay. So I think if you just go ahead and do some expansion out here, so what you do, I mean, I can actually show. No, I won't show. You can show. Can you show? Yeah, you just do some expansion, rewrite this as some summation, and then you will get it. Okay, I'm not going to do it, but you can show that you can actually prove that it's equal to Riemann zeta function. Okay, so I won't do that. So what next? What is it I want to do? Okay, so now further exercises for you. Okay, compute the variance in n. Okay, and also, so because n is this thing, so what you want to do is so define sigma n to be expectation value of n square minus expectation value of n whole square, and so the relative fluctuation would be sigma n divided by. Okay, so work this out, of course, and also uh, you can compute the variance in u by v. Okay, what is this related to? What is the variance in internal energy? Somebody? Yeah. Okay, so with that relationship, now actually the question which I want to ask is uh, what is the variance in n related to? Okay, it should be related to something. Okay, so if I recall correctly, it is related to compressibility. Okay, so look it up. Okay, so that's something which we should do. Okay. So I see the thing is that and then we know that sigma n square is greater than 0, and this or equal to 0, and this is related to stability conditions. Okay, so here, so if this relationship is true, this should be the same as saying that the compressibility is positive, right? That's the convention of stability. Okay, so this is something which you should. So and the proof is nothing specific to, not specific to the photon gas. Okay, so maybe I'll put this in the next problem set, but even if I forget to do that, you can just work this out. Okay, I think I'm out of things to say. I mean, there are a few more things, but I think that's better given in a problem set, so I don't want to discuss it. So we are kind of done with the photon gas. Okay, so next on the agenda, next is we will discuss okay massive bosons. Okay, so we just saw we saw two examples of massless bosons, one of which was the phonons, and I wrote phonon here, or photon. Okay, I wrote, okay. So we did phonons and photons, and now we will discuss massive bosons. And here we get something. Here we see something very interesting happen. Okay, and it's a phenomena which goes by the name of Bose-Einstein condensation. And what is this phenomenon? And the phenomenon says that below some critical temperature, Tc, which we will determine, of course, a macroscopic fraction of the particles okay, we know that at t equal to 0, so Tc, which is importantly greater than 0, at t equal to 0 everything goes to the ground state, we know that, but this happens before that. This happens at some Tc, okay, and this they are found in the ground state. So what does one mean? So let's say that let n0 be the number of particles in the ground state. Okay, then we usually expect so what do you expect if you take n0 upon v? What do you expect to happen? In some sense, n0 is a microscopic variable, right? So it is just the number of particles. In fact, I need not be take n0. I can take the first excited state or second excited state. So what we found is that that at high enough temperatures, most of these things are sparsely populated, right? So these n zeros will, so number density, of course, which is, this is not n by v. N is total number of particles. Okay, this is n zero, which is just the number of particles. So what is it you should expect? It should zero. It should go to zero in the thermodynamic limit. This is what we expect, and it's actually true. Generically, this is true. Okay, but in BEC, what happens is that okay. So this is the, so that means a significant non-trivial fraction. So what this, another way of saying it is that n zero by n is finite, because we know that when we take n to infinity, v to infinity, and n by v will be, number density will be constant, right? That's the thermodynamic limit. Okay, so both are extensive variables, but n0 is not supposed to be expensive. So this is what is happening. So this is a very counterintuitive. Okay, and this was predicted by Einstein, and like many things, we never thought that we would observe it, this thing. And so the only indirect example, only known example at that, for years after that, was that of helium 4. Okay, superfluid transition. And but that was sort of indirect, and there were some features of it which could not be explained, but it was gave a hint. Okay, however, this, of course, today this has been observed. Okay, and a few people have collected a Nobel Prize for experimentally observing it. Okay, and this again, these experiments are pretty remarkable, and so the story behind how they found it, and sometimes you need a little bit of luck or this thing. So there is some part of the story which is attributed to Eric Cornell, one of the people who got it, and so they had to create some kind of a bottle to hold the the condensate, and but they had a budgetary crisis, so they had to make do with a model which was not ideal, which fitted into their budget, and but it was nonlinear, and so they didn't know when they did it that whether the nonlinearity will help the cause or not help the cause. Okay, it's not so easy to do that thing, but it turned out that the nonlinearity, which so they see, the ideal thing is to have it linear where you understand everything and you can control things. But here in this case, it turned out that the nonlinearity, with hindsight, actually helped. Okay, so it's like the story of how many of these discoveries is done is not just people fluking it, but it's a lot of sweat, tears, and hard work, and and also being people being extremely clever. And so that's why listening to the Nobel Prize lectures, you would get to see vignettes of how these people had to, what kinds of efforts they had to put in to get to make these observations. And so you don't know whether it's going to work or not, and this is, so there are beautiful, so you can look up and you can see beautiful pictures of condensates. Okay, so I'll stop here, and next lecture we will start this whole story where we will study quantum bosonic gases, and we will see how this whole idea of condensation occurs. Okay, so I think I'm done for today. So, are there any questions or comments? No, you can't. No, you can't do that, right? I mean, then for large X it will not work. So, yeah, okay. So